Okay,
Yes.
so first of all, why are we learning this particular topic? Why? That's the very first question, actually. So, why we are learning?
Thermal physics. Why are we learning thermal physics? Probably because it there's some applicability. There's a decent amount of applicability of thermal physics. It describes a lot of things just in everyday life, but also, in other things. You have stuff like stars, you have just even boiling water that involves quite a bit of thermal physics, so,
See, the whole world is
the
behind.
application is wide.
See, the whole world is behind finding the alternative source of energy. Okay, like today, whatever source of energy we have, okay, whatever source of energy we have, be it the nuclear energy or be it the thermal power station or the hydroelectric power station, okay, be it any type of such sources, okay, there are two things. One, basically the energy conversion. So if you're talking about the nuclear power station or the thermal power station, so how do they basically convert things into the electricity? By converting the cold water into steam. That steam is causing the rotation of the turbine, okay, and
Yeah.
then the electricity is basically generated. Okay, then the other step comes, that is known as the efficiency. How much is the energy
Yeah.
input? How much is the energy
Energy
output?
in, energy out. Yeah.
Yeah. So that is the efficiency. Then, besides that, the formation of the star, talking about the solar energy also. So to understand all these things, you need to have a clear idea of the thermal physics. Okay, you need to have the clear idea of the gas laws also. Right. So in this particular topic, we'll be learning both the things. We'll be learning about what is the heat, what is temperature, and also what are the gas laws. Right. To understand all these things, we are covering this particular topic. What we'll be covering here in this chapter, the first thing that we are going to cover is the difference between the heat and temperature. This is the very first thing that we are going to cover. Let me tell you one thing. This is the easiest topic in the entire IB
Yeah. Yeah.
syllabus. Okay,
Yeah.
this is the easiest topic. Yeah. After this, we'll be covering the specific heat capacity. Specific heat capacity. Then we have the latent heat concept for the latent heat. Then we have kinetic theory of gases, kinetic theory of gases. Now here you'll be learning about the different gas laws, yeah, and a lot of things that is related to the pressure and energy of the gases. Okay,
Yeah.
so these are the things that we are going to cover here in this chapter, right? So starting with the very first thing, that is heat and temperature. So let's talk about that. Mhm.
I've gone over heat and temperature, specific heat, latent heat with Fahid, sir. Can we go to ideal gases immediately, or?
Oh, sure, definitely.
All right.
Okay, so I believe you already know what is heat and what is temperature and all that stuff, right?
Yes.
Yeah.
Yes.
So temperature is the measurement of heat. Is this the right statement?
No. Temperature is a measurement of average kinetic energy of particles
Yes,
in a
absolutely.
substance.
Yes, absolutely. Temperature is a measurement of average kinetic. See, the thing is, like, I'll teach you the gas laws. So I'm skipping the heat and temperature. I'm skipping the specific heat capacity, latent heat also. So should I directly start with the gas laws?
Yeah. Yeah.
Superb, amazing. So let's do it. So talking about the gas laws over here. So talking about the gas laws. So basically, the state of the gas is the function of the state of the gas is basically the function of pressure, volume, temperature, and the number of moles. Okay. Now over here we get introduced to the term called number of moles. What is number of moles? Okay. It's not a new thing. You have done this thing in your earlier grade also. Okay. So like we say 1 dozen. So what comes in your mind when I say 1 dozen? 12, right?
12.
1 decade, what comes in your mind? The number
10
10.
years.
Similarly, if I say 1 mole, okay, if I say 1 mole, so 1 mole is basically 6.023 into 10 raised to 23, a number. Okay. Now this is nothing but the Avogadros number. Okay.
Yeah. Yeah.
This is the Avogadros number. So the number of moles
Isn't it
basically.
6 point? Isn't it 6.023 times 10 to the negative 23rd? Or is it 23rd?
No, it is 23rd.
Okay.
Okay, right. So 6.023 into 10 to 20. Okay, let me tell you like how basically he came up. Oh, you also sneezing? I'm also having cold and fever.
Ah, okay.
Since last week only. I hope this is not COVID though.
Oh, yeah, you should probably get tested if that's a possibility.
I'm vaccinated, but like I heard people are scaring me that like saying that like even if you're vaccinated, you may get COVID. So
yeah, you should still get tested even if you have flu-like symptoms. Just get tested.
Tomorrow I'm planning to get tested because like it has been a week now that I'm not feeling well. Actually, yeah. Let's see. Okay, so we have this particular thing. So yeah, I was saying that like it was Avogadro who basically came up with this number, and basically it was not like he was sitting in the lockdown and like he was like counting numbers like 1, 2, 3, and then came up with the 6.03 into 10 to 23, that huge number, right? It was not like that. The thing is, he knew the mass of one hydrogen atom. So what is the mass of one hydrogen atom? It is basically 1.6626 into 10 to minus 24 gram. Okay, now hydrogen is the smallest and the lightest element, right? So so basically if you write in this form in the periodic table, it's going to be highly inconvenient. So he basically made this as a unit. So 1 gram. So 1 gram won't be having just one hydrogen atom. It will be having some n number of hydrogen atoms. So mass of n number of hydrogen atoms, n hydrogen atoms, that will be equal to 1 gram. So with that, he came up with this number n, which is with the unitary method is 6.023 into 10 to 23. Okay, so this is how this number was actually proposed. Okay, when you do the unitary method, you will come up with this number basically 6.03 into 10 to 23. Okay, so so here we can actually define that the number of moles is the number of molecules over the Avogadro's number. Yeah, is that clear? Any doubt in this?
Basically, Avogadro's number describes the amount of hydrogen atoms that make up 1 gram.
Absolutely, yeah. Okay, so this is the thing about the number of moles and the Avogadro's number. Any doubt in this particular thing?
Nope.
All right, let's go ahead. Now we'll try to understand the gas laws, and in fact, like some thing with the simulation also. I'll show you a simulation, but before that, like what is there in our syllabus? Okay, so so talking about the very first law, that is the Boyles law. Now this says that like if you are having a piston block system, let's say, okay, if we have this kind of piston block system, okay, so if it is having certain volume, let's say V1, right, and then if you are so it is having initial pressure P1, let's say P1, yeah. Now if you basically reduce the volume, so that will be possible if you increase the pressure, right? So if you're reducing the volume, so it will be having some different pressure P2, okay, then it will be having the volume V2, right? So what do you see? That if you're increasing the pressure, the volume is decreasing. So what we can say that P is inversely proportional to V. But over here, we need to make sure that the number of moles, that is the amount of gas, okay, number of moles, or you can say the mass of gas and temperature is constant. Temperature is constant. Okay. Now you may ask like, is number of moles same as the mass of gas? No. The thing is, number of moles and the mass of gas, they are directly proportional. If you increase the mass, so obviously the number of moles also increasing. Okay, like if I'm saying 1 gram of 2 gram of hydrogen gas, so that is equals to basically 1 mole of gas. Okay, if I'm writing 2 moles of gas, so it obviously will be having 4 gram of hydrogen gas. Okay, yeah, so it is increasing proportionately. Yeah, so the number of moles and the temperature constant, then P is inversely proportional to V. Okay, now here if I'm giving you a graph of P versus V, okay, and P versus 1 over V, how they will look like. P versus V will be like this, right?
Yep.
P versus 1 over V will be like this, correct?
Okay.
Now, a checkpoint. You have to tell me how the graph for ln P versus ln V will look like. Come on, tell me. What do you think?
If you do LNP, LNV, I mean, right now it's in.
You can
Just
annotate my
weird.
screen. Yeah, it has to be linearized, obviously.
Yeah, so it would be a downward slope, linearized.
So downward slope linearized like this, right?
Yeah.
Absolutely.
Yeah.
So basically, we are saying that P is inversely proportional to V. So we can say that P is equals to K over V. So we can say PV is equals to a constant K. So we can say P1 V1 is equals to P2 V2. Agree? Yeah. This is the equation.
Yeah.
This equation is held true only if the number of moles and temperature are constant. Yeah. So basically, whenever I say number of moles means amount of gas, means mass of gas also. Okay.
Yeah.
Number of moles, amount of gas, mass of gas are not same as the volume of gas. Volume will change for the gas.
Yeah.
Clear? Yeah. All right. Let's go ahead. Should I go ahead?
Hang on, I have to take this down.
All right. So should I go ahead?
Yep.
So here is a question then. If initial pressure is equal to 100 kilopascal and initial volume is initial P1 is this V1 is V. Okay. So if P1 is P, I'm just keeping it like simple. P1 is P, V1 is V. If pressure is increased by 20%, pressure is increased by 20%, okay, then calculate the percentage change in the volume. Percentage change in volume, given that N and T are constant. Okay, come on, do it. 16.67, isn't it?
Yeah, that works too. Rounding.
Okay. All right, cool. Yeah, true. Very true. Okay, let's go ahead. So the next law that we have, the second law. So that is basically the volume temperature law. Volume temperature law, also known as Charles law. Okay. The earlier one was pressure volume law, the Boyles law. Okay. This one is Charles law, volume temperature law. Now this says that V is proportional to T. The volume of the gas is proportional to the temperature. Again, if N and P are constant. Means the amount of gas or the mass of gas and the pressure is constant.
Okay.
Yeah. So what we can say is when we plot the graph for this, so this will basically look like V proportional to T. Okay. Now, if it is in degree Celsius, then it basically starts from here. Like at 0 degree Celsius, it is still having certain volume. Okay.
Yeah.
Yeah. So when you basically extrapolate it and make it meet x-axis, the temperature axis, okay, you will find that this is basically minus 273 degrees Celsius.
That's 0 Kelvin.
0 Kelvin. Yeah. So that's how the Kelvin temperature was basically proposed. Okay. So at the same time, if I'm writing this T in Kelvin over here, then this will be a straight line from the origin. Okay. Is that clear?
Yeah.
Now, we can say that V is equals to KT. K is a constant. So V over T is a constant K. And we can say V1 over T1 is equals to V2 over T2. Right. So this is another equation that we got. Okay. Any doubt in this?
No, no doubt.
All right. I'll give you a few more questions later, like once I'll finish all the laws, right? There are two more basically. Okay. So the third one is the pressure temperature law. Pressure temperature law. Okay. And this is known as Gay-Lussac's law. Gay-Lussac's law. All right. So the pressure temperature law. So this says that P is basically proportional to the temperature. Okay. Given that if number of moles and the volume are constant. Okay. You can see that all the things are like revolving around P, N, V, T.
Yeah.
Yeah. So, oh, your dog is barking. What's his name?
Carmelo.
Carmelo. Yeah. Nice.
Yep.
Very chocolatey name.
Yes. Yes. He was originally named. He was originally named Caramel by the place we adopted him from, but my dad changed it.
Oh.
I don't know.
Wow. Nice. All right. So again, so basically here we have this pressure temperature law. So when we plot again, like if it is with degree Celsius, then again this will be having this kind of graph. Okay, where this is again like 0 Kelvin, right? And then this is the T in Kelvin, and this is the pressure, right? Again, I can actually write the similar expression over here that P is equals to KT. So P over T is a constant. So P1 over T1 is equals to P2 over T2. Yeah. So this is a thing. Yeah. Any doubt?
Yeah. Yeah. It's basically the same thing over and over again with different numbers.
Exactly. Yeah.
But then I'm assuming there's one unifying formula for all of these.
Yes, right? I'll come to that. Don't worry. I'll come to that. Okay, so the last thing, the last law that we have, that is the fourth one. And that is the Avogadros Law, basically. Avogadros Law. And this says that V proportional to N. Means the volume is directly proportional to the number of moles. Okay, given that P and T are constant. Okay, so the volume will increase with the number of moles. Okay, and there is a if you people have learned in earlier grade that 1 mole is equal to 22.7 dm cube. Okay, in IGCSE they learn this thing as 24 dm cube. 1 mole equals to 24 dm cube at room temperature pressure. This one is at standard temperature pressure. So you must have done this thing if you have taken chemistry earlier. Did you?
No, I haven't taken chemistry really.
Okay, all right.
I just didn't like it that much, I guess.
No problem. So 1 mole equals to 22.7
dm cubed is referring to decimeters cubed.
Yes, and that is equivalent to 1 liter. 1 dm cube is equals to 1 liter. Right? Yeah.
Yeah.
All right. So volume proportional to the number of moles. So you increase the number of moles. So obviously the volume will also increase, given that you're keeping the pressure and the temperature constant. Okay. I'll show you all these stuff with the simulation also later. Okay. So here we have V proportional to N is like this. You increase the number of moles, volume also increases. So you can say that V 1 over N1 is equals to V2 over N2. Okay, because V proportional to N, so V over N is a constant, so V1 over N1 equals to V2 over N. Yeah, when I summify all of these, when I basically summify all of these all together, so what do we see? That some in the first law I wrote this as P1 V1 equals to P2 V2. Then I wrote V1 over T1 is equals to V2 over T2. Then I wrote P1 over T1 is equals to P2 over T2. And then finally, I wrote V1 over N1 equals to V2 over N2. When I combine all of them all together, then this becomes P1 V1 over N1 T1 is equals to P2 V2 over N2 T2. Agree? Those are now in this particular final equation, whichever thing is constant, you eliminate that term and you will get that respective equation. So let's say like Boyles law. So in Boyles law, the number of moles and temperature constant. So you can actually remove both of them, and then you get this Boyles law
Yeah,
equation.
P1 V1 P2 V2.
So basically, this is a kind of the, you can say, the master equation, yeah, for the gas laws. Yeah, no, no, I'm having it since morning. Today is like horrible day for me. So PV over NT is equals to R, a constant. Okay, since we are saying P1 V1 over N1 T1
Yeah,
equals to P.
yeah.
So this is a constant. This is known as universal gas constant. This is known as universal gas constant. So with this, we can say PV is equals to nRT, the very famous ideal gas equation, right? Have you come across this
Yeah.
equation?
Maybe. I don't know. I don't
Yes.
think so, actually.
Have you done this chapter in school?
No, we haven't started ideal gas laws yet, which is why I was asking about it.
Oh, okay. All right, so this is something that you will be covering, okay? Like they'll directly give you this equation actually. Okay.
Yeah. PV and RT.
Yeah, so PV equals to nRT. This is the ideal gas equation. Okay, a very, very important equation actually. Okay, the thing is, here I'm using the word ideal gas. This means this is not for the real gas. Okay.
There are certain assumptions made for ideal gases that are
a lot of assumptions, which we'll be learning while doing the kinetic theory of gases. Okay.
So then, do ideal gas models actually work? Or
ideal gas don't exist. They don't exist.
Yeah, but I mean, for predictive models, do they work?
So there is just different equation basically. Now the thing is, why still we are learning about the ideal gas? Because like this is actually giving us a base to understand how the gas behaves. Yeah. So there is another equation which is not in our syllabus. I'm giving you that equation. P plus n square A over V square into V minus NB is equals to nRT. Now this is the actual equation. This is for the real gases. Now this is not in our syllabus. You don't have to bother about this particular thing. This is the real gas equation actually. Okay. Over here, small a and b are constant and they have some specific value actually. Okay. Right. So this is the actual
value specific to specific gases.
Exactly. Yes. For hydrogen, it is a different value. For helium, it is having different values like that. Yeah. So so this is the actual equation. This is the real gas equation. Okay. But this is this is something which we don't have in our syllabus. Okay. So we will stick to PV equals to nRT. Okay. And all our questions will be based on PV equals to nRT only. Now I'm giving you some graph based questions right now. Okay. You have to tell me the answers for that. Okay. So let's do this. So here we have P versus T, and these are at different volumes, V1, V2, V3, N is constant. Okay. You have to tell me what is what should be the order. You need to use the sign like this, obviously. Yeah. So this is the question. Come on, tell me, what do you think? Yes. See, the thing is, so V1 is the smallest, V3 is the largest. Now, see, the thing is, your logic was good, but it can be solved in an easy way, okay, in a mathematical way. So since we are having three variables over here, pressure, volume, and temperature. So let's make one variable constant, okay? So you tell me which variable should I make constant? I cannot make V1 volume constant because that's, yeah, so let's make T constant. So I make T constant. So in this particular line, it is having the same T, right?
Yep.
So this is corresponding P1 over here. This is corresponding P2 over here. And this is the corresponding P3 over here. Now, by seeing the pressure axis, I can say that P1 is greater than P2, greater than P3. And the relationship between pressure and volume is inverse. PV. So V1 is less than V2, less than V3. Simple. Cool.
Okay.
Yeah. Why? Because volume is inversely proportional to P, isn't it?
Isn't it P1 V1 or PV P time? Oh
Yeah. So
yeah,
P
that
times
would
V is a
that would make sense.
constant.
Yeah.
Yeah. So
Yeah. Okay,
yeah.
my bad. So P is equal to K over V. They're inversely proportionate. My
Yeah.
bad.
Yeah. You got it right. Should I give you the next question?
Yep. Yeah, sure.
All right. So on the similar lines, I'm giving you here another question. Here you have P versus 1 over T. Okay. And you are having oh why P versus 1 over V at these different temperatures T1, T2, T3. Okay.
Okay.
So T1, T2, T3. Yeah. So what do you think? Should I use like which sign in these boxes? This T1 is again straight line only. So don't.
Yeah.
Okay. So here another question, mathematical. So uh, so initial pressure P1 is equals to 100 kilopascal. Okay. Let's work with the
Okay.
numbers. V1 is equals to V1 is equals to 20 dmq. Yeah. And and T1 is equals to 300 Kelvin. Yeah. So for the same volume of gas, for sorry for constant n, for constant n. So if the pressure is doubled, okay, P2 is equals to 2 P1, V1 is equals to V over 3, okay, V1 over 3. So what this T2 would be? Yeah, come on, do it. Then I'll show you the
Okay.
simulation after this question.
Yeah. So if P2 is equal to 2P1, so then 0.2
Substitute
over
P1.
10 to the yeah, I'm just solving for T 0.6 or no, just 6 times 10 to the third. I'm probably decimals for this because I guess I don't know how to do basic math.
You
Times
know
10 to
everything.
the oh, it's 10 to the 6th. Why am I? Oh, it's 10 to the 6th over 6 times 10 to the third. Yeah, I'm getting 200. I'm getting T2 as 200.
You're right.
It's right.
Yes, absolutely.
But that doesn't make much sense because
Why not?
should the temperature increase? Well, that depends. Oh wait, but the temperature will decrease because N and R are constant, but we have 2P1 or 2 times 1/3 into PV.
You're applying pressure
So
and you're compressing the thing, so that will
yeah, I
cause
know. I'm just
cooling.
thinking about it mathematically. I know. The thing is though that essentially 2 times 1/3 into P times V is what we're essentially doing, and that's 2/3 PV. That's yeah. So the overall output with NR being constant means that the temperature will decrease. Yep.
This is
Okay.
simple way. Yeah, like you could have got it like
The
in a
thing
minute.
is that I know. I just got a little bit confused, I guess. But the other thing is that I've seen some videos wherein they compress a gas and the gas heats up.
Yeah, that's a different thing. Let me give you the question with that. Okay. All right. So here is a question. So basically, uh, again, like a similar kind of situation. I'm giving you P1 as P, then V1 as V, and T1 as like 300 Kelvin again. Okay. Now what I'm doing, P2 is equals to 5P. Okay. And then V2 is equals to V over 10. Okay. Then determine T2. Come on, do it. No, actually, yeah, you are right. But like, I actually wanted to cause the expansion. Okay. So basically,
So
if
then the ratio
suppose,
between so if you want to cause expansion, then
let's say P3 is 5P, V3 is 20V, then T3 gonna be equal to 300 to the 600 Kelvin. Okay.
Yep.
Yeah. So all these things are basically used in the gas thermodynamics in the Joule-Thomson effect to like this on the basis of which the refrigerator or the air conditions they basically function. Okay.
Yeah.
Yeah. All right. So we'll see that later. So let's go ahead. So now I want to show you the simulation, and then I'll give you some questions from your textbook itself. So here, let's understand each and every element in this particular simulation. So this is the thing with which you are basically introducing the
Pumping in
gas
air. Yeah.
in the container. Yeah. Then you will see the thermometer 300 Kelvin and the pressure gauge over here, which is showing the pressure, kind of fluctuating pressure. Yeah. Now this is the heating source. This is the heating source, and it can be used as a cooling source also. Yeah. You can actually relate this width with the volume, like since it is the two-dimensional thing, so like we have to stick to
hang on, I can probably find this on the FET
yeah, it's there on FET
for
only.
myself as well.
Yeah, this is for FET only.
I'm just going there to find it.
Just go on FET, type gas properties.
Yeah. Gas. Oh, yep. No, gases intro.
Not the intro, like go with the properties actually.
Oh, okay.
Yeah. Now, what I actually want to show you over here is the verification of all the laws that we saw today. Okay, that is the Boyles Law, Charles Law, Gay-Lussac's Law, and the Avogadros Law. Yeah. So here, this 10 nanometer over here is basically representing the volume. You can say 10x is the volume. So if you decrease it, so 5x is the volume. Okay, you increase this, 15x is the volume, like that. Okay. Yeah. All right. So now let's keep it at 10 only right now, and let's do an experiment. Okay. So what I'm doing here, I'm keeping the pressure constant and changing the volume with the varying temperature. So
also,
see,
are you running? Okay, you're running ideal.
Yeah.
Cool.
Okay. So now when you heat it, please observe, like right now the temperature is 298 Kelvin and the pressure is 39.3 atmosphere and the volume is 10 nanometer x, 10x you can say. Yeah. When I heat it, you see the temperature increased with 330 Kelvin. Okay. Temperature increased with 330 Kelvin and then the pressure volume is 11.1x. For the 362 Kelvin, volume is 12.2x.
Yeah.
So, and then after 5 trials, when you plot the graph for volume versus temperature, you'll observe that it is basically a kind of straight line. You got that?
Yeah.
Okay. So this is a very good experiment. Okay. To collect the kind of close to realistic data. Okay. But like these are not realistic data though. All right. Yeah. All right. So this is like all these things working on the Java and the simple
HTML5.
HTML. Yeah. Okay. All right. So going ahead. So now this was like the variation of volume with the temperature. Okay. We will change it and then again we'll be introducing the thing and you will be doing the experiment further after this. Okay. You will be introducing like good amount of gas in it. Okay. And then make temperature constant when you're changing the pressure. Okay. When the temperature, pressure constant when the temperature will be varying. Okay. So, so here when I'm introducing more to it. Okay. So suppose here we are introducing more to it. Yeah. So you can see that the 217 Kelvin. Right now the temperature is 217 Kelvin. Now if I increase this thing, I need to show the width. If I increase this, you see with the increase in the volume, the change in the temperature and the pressure is to be seen. Yeah.
Yeah.
So you need to note down all these stuff. And then when you plot the graph, you'll get a like really good graph basically. Okay. You see with the change in volume, like the temperature is also changing. Similarly, you can actually make other things constant, like let's say temperature kept constant, and then in that case, at the constant temperature, pressure is inversely proportional to volume. So what will happen? Like if you're putting more, like if you're decreasing the volume, pressure is changing. If you're further decreasing the volume, pressure is changing. And if you're increasing the volume, pressure is decreasing. You can see that, right? Yeah. When the temperature is constant. Yeah. So likewise, you can actually do all of them. Okay. All the 4 laws of gases. Okay. And you can collect good number of data. Yeah.
Yeah, okay. Just keep it.
So I hope this is clear.
Sorry. Yeah.
No problem.
Yeah, that's clear.
Yeah. So will you do this experiment yourself and collect some data?
Yeah, I guess I can.
You have time. See, I feel that like you have time. You can actually do this experiment yourself, collect some more data.
Yeah.
We are anyways ahead of the school. Okay. So in our another session, we'll finish this chapter. Okay, and then we'll be doing some questions. I'll send you the worksheet though. Okay, I want you to do that worksheet. Okay, before the next class. Okay.
Yeah.
Yeah, as much as you can. All right. Okay. So see you then. Bye bye.
Okay, bye.